Test, test, test. Yes, if you give you that, it is
Don't make any jokes.
Sorry?
Don't make any jokes about wind rosing. Oh no, Shri, you can. Pretend to speak and say, "Can Shri hear me?" This is there a pointer or a?
Yes, there is. There's a pointer and a left.
Oh right, okay, great, thanks.
I will load the slide.
Okay.
I'll need that before you. Okay, everybody, good morning. So before we start day 2, I just have a couple of quick announcements. I wanted to follow up on an excellent suggestion by Melissa yesterday that I know a lot of you are thinking about proposals, and that's great, and I want to encourage collaboration. So if you are interested in recruiting people to your team, or you have an idea that you would like to share and get some feedback on, I want to encourage you to make a pitch idea. This is a very short presentation, maybe just a minute or two, and if we have enough takers, we will do this in the discussion session at the end of the afternoon. So if you go to the meeting website, and that is the short link to the meeting website, you will see a media tab, and you'll see that all of this are linked under this area here. And I've added a pitch document, so you'll see a set of presentation slides. It looks like this, and I want you to fill in your idea, your contact name and email, and a quick outline of just bullet points of what your idea is. And we will go through those and give you an opportunity to stand up and talk to everybody about it later on this afternoon. With that, I will hand over to the session chair, Dimitri Duet, to introduce our first speaker.
Morning, everyone. So we have Matthew Graham now, who will talk about CTF.
Okay, thanks. I'm the first M. Graham up this morning. You know, I went through 7 years of school with someone also called Matthew J. R. Graham. I'm just Matthew J. Graham. And I thought that's terrible, and I thought I'd escape that. And now, of course, I come to astronomy and time domain astronomy. And I often get emails from Melissa addressed to me, and I imagine she gets the same. So anyhow, yes, so I'm Matthew Graham. I'm the Ctf project scientist. I'm a research professor at Caltech. And I'm going to give you a sort of status overview, highlight some of the things that are relevant for this audience. So for those of you who are sort of unfamiliar, Palomar Observatory and Caltech, we've been focusing on developing a sort of time domain astronomy ecosystem for about the last 15, 20 years. So and even longer, in fact, and I'll sort of talk about that in a minute. So we have our main discovery engine is the 48-inch here, and here's the 60-inch where we do follow-up with the spectral energy distribution machine, which is a small IFU, and then we have the 200-inch, Hale's big telescope, complementary to the ones that Chris Burns was talking about yesterday, for classification. So we can do the sort of nuts to bolt story, or the photons to papers story, all within one mountaintop, which is, I think, is where we're all doing. So the main discovery engine is the 48-inch Samuel Oskin telescope. It's a almost 70-year-old system now. In 1950, this is a Bugatti 101, top speed 120 miles an hour, one of the fastest cars in the day. And here we are 70 years later almost. This is a Bugatti Chiron, which a month ago broke the 300 mile an hour barrier. So in terms of car speed, in terms of technology, if you want to use that as a metric, we've managed to increase our speed of getting around by almost a factor of 3, sort of 2.5. In terms of survey speed, though, with the same telescope, we are about a factor of 1,300 faster in getting data and collecting the sky, because we've transitioned from photographic plates to large format CCD detectors, robotic telescopes, dedicated data pipeline systems. So astronomy is currently outstripping the major industry, and long may it last. Of course, the thing we're all looking forward towards is LSST, and what you can view ZTF as is about a 10% LSST, or a 1/30th depending. Interestingly, the numbers that Steve was showing yesterday for the dollar costs of LSST, it's about a 30th as well, or even smaller. So, you know, our total cost for ZTF is about the $25 million budget, times by a factor of 30, you get to $650 million, which is sort of the LSST cost. So it's about a factor of 10 to 30 in a lot of ways. Specifically, number of sources, we've got of order 1 billion, maybe 2 billion sources that we cover, trillion detections through the alert systems, pixels. The ones that are probably relevant for the transient astronomy is this nightly alert rate. So we put out roughly 1 million alerts a night. LSST will do more. And so this has been one of the main drivers for ZTF and its community engagement. And ZTF trying to get the community ready for LSST and sort of saying, okay, we're going to give you the alert stream that you can play around and build on to get ready for this factor of 10 increase. And you can think about how you need to scale up and what else you need to develop to work in that area. This is the Ctf Field of View. Obviously, it's a much smaller telescope, so we can get a much larger field of view compared to LSST. We go to about 20.5. They'll go to sort of in the single observation, 30-second observation, 5 sigma. LSST will go a few orders of magnitude deeper. But this large area means we can cover the sky very quickly. So this is a shot inside the tube. Let's see if I can get this to play whilst I'm talking about it. That play? Yes. So what we have is, here's our big shutter at the end, mechanical shutter, opens and closes in. So this is doing a filter exchange. We don't have a filter wheel. We have a robotic filter arm actually in the tube. So we have a cassette deck down here, which holds these big filters. It holds a G, an R, and an I filter currently. And we park the telescope in a safe position. So here's the camera. We have a raft of 16 CCDs. Each CCD is subdivided into 4 quadrants. Each one of those quadrants is the unique element as far as data processing and discovery is concerned. So we essentially have 64 independent elements when we do reference building, photometry build-up, that sort of thing. It takes about, just over a minute to do one of these filter exchanges, so we can do multiple filter exchanges in a night. Typically, we schedule blocks of observations in the same filter because we know that in an hour we probably can do a maximum of about 20 filter exchanges, but that means a lot of time is lost to slewing the telescope to a safe position because Palomar Mountain aren't very keen about us having a robotic arm changing pieces of glass above a nice mirror in an earthquake zone. So they want it to be, if something. Now, there's a lot of redundancy built actually into this system. We have mechanical latches, we have electromagnetic sensors and such. So it's actually testably proven that it needs to be a really big shake. And it'll probably damage the building more than it would the telescope. Anyhow. But you see, it's nice and compact. Everything sits out, and so that's essentially the mechanics of the ZTF system. So the way we are funded is that we are a private-public or public-private partnership. NSF provided money through the MSIP program, which is about 40% of our funding. We have a ZTF partnership, which provides about 40% of the funding, and then Caltech provides the remaining 20% of the funding. That means that we have 3 separate observing programs. We have a 40% public observing block. We have a 40% private partnership observing block, and then we have a 20% Caltech observing block. The 20% Caltech observing block just goes into the regular Caltech TAC, as does the P200 time and Caltech Keck time. The partnership define a number of observing programs that they want to address, and those go in place on a basic semester basis. And then the MSIP time, the public time, has been devoted to visiting the northern sky every 3 nights in GNR. So we do about 4,000 square degrees on average per night. And then there's also a galactic plane survey where there's a nightly sweep of the galactic plane and what's available, what's observable, again in GNR, and that's about 1,500 square degrees a night. So what you build up is these nice coverage maps, and obviously you'll get slightly better coverage in the galactic plane because that's on a nightly cadence. We average about, there's a bit of tail in certain fields where the scheduler and weather constraints and whatever means that maybe it's not typically 3 nights between them being coverage, but on average, we're at 80% for a given region on sky being covered at least once every 3 nights in GNR. So it means you get the 2 data points and you'll get a color with at least half an hour between them, because for the moving object for asteroid rejection, a night. And that's the data that forms the basis of the ZTF public alert stream and the ZTF public releases, the data releases. So we put out these alerts. We started June last year. We used this, so University of Washington are one of our partners, and they were very interested in developing or testing an alert system with an eye to Lsst, obviously. And so Eric Bellum's been leading this work, our survey scientist. So we use this Avro binary format, JSON format, and we distribute these events using the Apache Kafka system, which is an industry messaging standard. Why bother inventing one of our own when there's stuff out there which is supported much better? And I say that as one of the original designers of the VO event protocol. It's great we can invent things and we can invent binary transport formats of our own, but if there's something industry that already does it at scale, we don't need to solve those problems. We can just take them and see if we can use them. So one of the a ZTF alert in this Avro format, you get 3 images. You get the discovery image, you get the reference image, and then you get the differential image subtraction coming from our pipeline. These are 63 by 63 pixel 32-bit images. The reason it's 63 is because that seemed to be the largest or the smallest number that the machine learning folks wanted at 32-bit resolution when we were doing experiments with this about 2 years ago. And we have stuck with that format and size because there's downstream stuff that's attached to that. You get a 30-day rolling window light curve history, and including null detections. You get a spatially unique name. If there's been a previous transient or previous detection within 1.5 arcsecond radius, it'll share that name. So that's how we do a spatial aggregation of individual detections to build up associated data. Obviously, that may not be particularly true in very crowded fields, but that's, it's a best effort. We also include a whole load of metadata, all the parameters from the Zogia detection, this real bogus score, star-galaxy separation, distance to the nearest 3, or the details of the 3 nearest Pan-STARRS 1 sources within 30 arcseconds. We calibrate to PS1, the nearest solar system object, and an alert history. So more details about what each of these would be previously, so you can build up. So that's what we send out in this format. If you're interested in getting alerts, so we have MOUs with a number of things. The reason we have an MOU with a broker is just so that we can establish, we will give you this and you will provide to the community that. It's nothing more than that. It's not that the brokers get any sort of private data streams or whatever. It's just to establish what our expectations are of something that is putting our data out to the community. So LCO Mars was the first one, not really intended as a full broker. Antares, Lsst have all come on in the last year, and you'll hear talks about Antares and Lsst later today. No one here from Lsst, unfortunately. And the University of Washington have a bulk thing, so they put out nightly tarbles of our alerts for the public. So some of them offer basic web searches, some of them allow you to do user-defined filters, either in real time or non. Some have notifications. Antares allows you to get alerts on Slack. You'll hear more about this, I guess, from the demos you'll see later. Some do Kafka streams, so some have a sort of downstream sending alerts that match what you've already seen. Some have APIs. Some allow you bulk access. So there's a range of different functionalities that they're offering. I think that's an important thing, that different brokers offer you different things. It's not as though each broker offers you exactly the same, and so you're just going to go maybe for your geographically nearest one. Some of them have different ideas of what they want to do or what they want to serve or a community that they're addressing. And so there are reasons why you may be connecting to different brokers as a TOM to get the same alert or different variants on the same alert. Right, so since last June, we've put out about 180 million alerts total. Of that, 56, 57 million have been in the public alert stream. This is our sky coverage from the public data, or total data, all data. So this is what goes into building the reference images. So we have full sky coverage in the GNR. The I-band data is reserved for partnership time at the moment. They paid for the I-band filter. But that data will start to become public in the next data release. Supernovae putting out, we register a lot of them with TNS. We have a bright transient survey program. So a lot of the anything brighter than 18.519, we try and get a spectrum with it with SEDM for the follow-up. That gets registered with TNS. We make those alerts, that information available in public in real time. Same with the spectra, so doing the community, TDs, asteroids, pick your science, we've got stuff going on. We had our first public data release in June. We put out the light curves for the for the 2018 data for 1.2 billion sources. The next public release, we're on a 6-month cycle now, so the next release will be DR2, which comes out in mid-December. That will include all the data from the first 6 months of this year, plus the first bits of data from the Caltech and the partnership time. There's a proprietary period of 18 months on that data. So all future data releases now, you will start seeing data coming from those observations or programs that were defined from that as well. So it's not as though we will be sitting on 60% of the data forever and it'll never see daylight. It'll see daylight after 18 months. So the I-band data will start to become available there soon. Since July, we've been co-observing with tests. So this is partly public time. This is partly a bit of Caltech time. So each night we do GNR of the test fields of the current test sector. We put out nightly alert tarbles of this information. They also go into the nightly alert streams in the public streams, but if you just want the tarbles. Also, within a month of each sector ending, we're putting out light curves for those observations in the sector. So we did the September 15th, we did the sector 14. You should expect sort of the end of next week, the sector 15 one, and we're moving on to sector 17 tracking. So there's sort of a 2-month that way. Huh? Just a couple of the brokers which are now actually not only redistributing, but actually doing stuff with what we put out and doing science beyond what we are doing. Lsst is reporting single image supernovae in the Ctf public streams of TNS. So whereas we typically require 2 observations, they do 1. 601 as of last night, 56 has been spectroscopically classified. Really good for people who want to do those very fast transient detections. Antares itself, I guess you'll hear more as well about this. Lots of users, they're putting out ATELs and stuff that they're finding. Again, this is stuff that we're not doing. It's stuff that the community is now doing on the public stream with the brokers and science that's coming up that way. A couple of in-house things that we've made available. So we have this big piece of infrastructure underneath a lot of what we do at Caltech called Kowalski, and that's available on DEMA's GitHub repository. this is a sort of Swiss Army knife. This is our database infrastructure. We have things that look like TOMs or look like brokers or look like something in between that sit on top. So we have a ZTF Alert Lab, which does a lot of the things you may be interested in. Yeah, all sorts of things that you can do. We use Google Colab for hosting Jupyter notebooks. Those are available for anyone to download and run. There's a tutorial which we put out for how to do ZTF alerts triggered in the test fields, filtering public alerts. That stuff's all out there for you to go and look at and see how to work with it. If you want to do your own installation of Kowalski, you can download the stuff, or it's Dockerized. You can talk to Dima. Zwikiverse, we do some citizen science, or we do a lot of labeling for our machine learning. So we built this piece of infrastructure to speed up the learning on that. Again, talk to Dima or whatever. We have two significant pieces of machine learning that form part of the alert stream. The first is this deep streaks. These are convolutional neural networks that we use for the asteroid detection. There's a paper about this early from this year, written by Dima. I'm not going to talk much about this. It's just that we have really high positive rates on this, and what's more important is that near real-time operations. Previously, it was taking human scanners several hours each day to go through the asteroids, candidate asteroids, that the machine learning that the old random forest classifier was doing. Running this deep learning one now, it's less than 10 minutes a day, and this thing also is finding new things. One of the other things we put in July is BRAI, which is our new real bogus classifier. We previously, again, we inherited a random forest version from PTF, which seemed to do okay, but not brilliantly. So based on the success of deep streaks, we went forward with, a deep learning architecture. And this is now included as it's the DRB piece of metadata and all that's much, much better. And the performance is significantly better. So it's a 0.5% false negative rate versus a 20% false negative rate from the two systems. Again, there's a paper out on this, so you can read about the details of this. It's just that deep learning really seems to do well with the images, and there are all sorts of experiments we're also trying with that sort of in place. One of the interesting things that's driving both deep streaks and BRAI is that we are looking at cost-effective machine learning. So you can buy these devices called TPUs, which are sort of like GPUs for machine learning, TensorFlow processing unit. They cost about $100. It's a little USB thing that you can plug into a Raspberry Pi. So you train your model on Google Cloud or something like that. You download the trained model. You put it onto this little device. You plug it into your laptop. And then you can process a night's worth of ZTF alerts in about 5 minutes. So you can imagine if you buy 10 of those, you've got each one trained for a different model for $1,000. You've got a really nice supercomputer that's applying 10 different models to your thing and streamlining and all sorts of things. So I'll leave it there. Okay.
Perfect time. We have a couple of minutes, and please ask questions. But before you do that, could everyone please move to the center to allow for people who are waiting maybe outside to sit? And also, the session is being broadcast in the foyer, so if you would like to sit there, you can also do that as well.
You said about 2,000 and something classified transients. What the source of this classification? Are they spectroscopically classified and then human classified, or is
this set here?
No. On the middle of the slides somewhere.
On the TNS, yes. So that's where are we? That's coming from the Lsst. So these figures.
There was something like 1001 A supernova in the middle of your presentation.
Right.
Earlier.
Yes.
Here.
Yeah, these are all spectroscopically confirmed.
Yeah, and then classified by by whom? By human. Every of these 2,000.
Yes, a lot of these are from the SCDM, or mainly from the SCDM. So they go through there's a pipeline but then there's human verification that these are.
Thank you very much.
Okay.
That's mainly from the growth marshal, so there are filters on the growth marshal that feed on the alert stream.
But then, as Mansi was saying yesterday,
Yes.
the alerts can be automatically put into the onto the queue for the 60-inch or other time that we have available.
For moving objects, do you have, are you feeding the astrometry to the Minor Planet Center?
Yes.
And do you have alerts going out for when things become active?
Yes. Yes, so there's a whole separate pipeline that we have for moving objects. The Solar System Group are a very active group, and they're putting out a lot of stuff. But anything we detect does go to Minor Planet Center, and we double-check with Minor Planet Center as well for the moving object pipeline.
I was wondering if you could say what was what fraction of the transients are you reporting to the TNS? Or like, what is the threshold for that?
So we have, Mansi as well, I think, mentioned yesterday Ampel, which is a project that comes out of DESI in Germany, in Berlin. It's a sort of automated broker classification engine. They're the ones who are largely feeding TNS with things that they believe are high probability transient events. I'm not certain what the rates are, but it's certainly a few tens a day, I think.
Would there have been a problem if you just like fed everything into the TNS?
Well, so we could put 500,000 to 1 million alerts a night into TNS. I don't think TNS would be very happy with.
But not distinct transients, right?
Each of those may be a distinct transient.
And can the TNS not handle that rate?
Well, probably. Well, with scalability, yes, it could. But then you wonder what the utility is in having. I mean, most of those are going to be variable stars.
Okay, that's a good point. The reason for my question is like the TNS is supposed to kind of solve the problem of having to look at all the different surveys individually and like aggregate transients. And I find that I now still have to do that because I have to aggregate everything from the TNS plus some ZTF broker. Right. So I just was wondering if there's some way of solving that, or I don't know.
So if you go to Antares with button of TNS, so you can just click and then you'll see the association. So we do that for you.
Well, it has everything from the public alert stream. Yeah, but I mean, that's the idea of a broker. So a broker is supposed to maybe aggregate things, and so, you know, Lsst is looking at 15 brokers to do this. And a lot of them are working with ZTF data as well, so, but then you have to look at 15 different brokers instead of just a single place. I mean, but no, I think TNS could do it. I'm not certain they politically want to, because it washes out a lot of, you know, they want things that look real and are interesting potentially, instead of just, here are 400,000 observations of variable stars again. And then you get into the classification, and then that's another issue.
Right, we have to move on. Let's thank Matthew again. And now we have Melissa Graham, who will talk about the Lsst.
Hi everyone, my name is Melissa Graham, and right now I work for the Lsst at the University of Washington, which is where most of the prompt pipeline is being put together. And I work there with the data management team as a science analyst, which means my job mostly falls under the category of science validation of the data products. So I'm always interested in figuring out what kind of science people will want to do, and then make sure that the data products that are being planned and developed will be appropriate to do that kind of science. So that's why I'm here, to tell you about the data products to enable your future science. I just want to tell you briefly about University of Washington first. So my particular science background is supernovae. And so one of the ways that I'm involved in sort of the follow-up ecosystem right now is using the University of Washington's Astrophysical Research Consortium, the ARC 3.5 meter telescope at Apache Point, which is really well suited for time domain astronomy. It has all of its instruments hot and able to do an instrument change in like 30 minutes or less. Has a really reliable GUI for remote observing from anywhere, and accepts all kinds of TOO and DD requests. So, and also they asked that I point out that leasing time is available on the ARC 3.5. If you are trying to do some research, some follow-up program, and you're looking for something that's really easy for remote observing and can handle your kind of science, this might be of interest to you. I find it's useful. For me, I've been following up like Ctf alerts, for example, right now. And so, and also later, I'm going to pitch a TOM that will be in service of this kind of observing also. So, Lsst. I'm going to tell you, I'm going to give you a brief status update, show you some pretty pictures of things that are being put together now. Then I'm going to tell you about the data products, because if you're designing TOMs, you're probably going to be interacting with the Lsst data products at some time in the future, such as the alerts, or maybe writing like an API piece of your TOM that goes and queries the Lsst catalogs to get more information or cut out image stamps or something like that. So I want to tell you about the data products as well to inform your TOM development here at this workshop. So in case you have never heard of the Lsst, this is sort of a one-page summary of the hardware and the main survey that the Lsst will do. So up in the top left is the camera, the focal plane, and you'll see all the CCDs there. And one 3x3 set of CCDs is called a raft, and I will refer to that again later in the talk. And the total field of view of the Lsst is, of course, 9.6 square degrees. It has 6 filters, UGR, ICY, and most of the time will be spent on the main survey, which is also called the Wide, Fast, Deep survey. There's a whole bunch of sort of stats about that survey there, about 18,000 square degrees, 30-second images that go to a R band of 24.5 in a single visit, and then 10-year depth is 27.5. Survey start should be late 2022. As far as I know, we're still on track for that. And in addition to the main survey, there's also a bunch of special programs, mini surveys, twilight surveys, and the deep drilling fields, which you might be interested in also for your particular science. That's like a one-slide overview. And here's a picture from just a couple of weeks ago showing that the dome is getting covered, which is very exciting. So back in August, and every August actually, we have the Lsst project and community workshop that brings together people working on the construction project, building the hardware and the software together with members of the community that are going to be using the data in the future. So here's all of us. I just want to bring you up to date on some sort of most exciting highlights from that meeting. The first is that all of the CCDs have been delivered and that rafts are being integrated at Slack. So here's a picture of the camera from just a couple of weeks ago. You can see that the rafts are being installed, and so camera development is progressing. The other nice highlight is that the single raft commissioning camera, which we also call ComCam, is in lab testing in Tucson and is anticipated to arrive at the summit in early 2020. So there's ComCam with its single raft ready to go in testing and already providing sort of useful data like what do the biases look like and that kind of thing for the CCDs. The telescope mount assembly, which you see here on the left when it was in Spain, where it was assembled first and subjected to some testing, it's been disassembled and shipped to Chile and has arrived and been transported to the summit. So all the pieces needed to hold the mirrors are there, ready to be put together once that dome is covered. And the last highlight is that all of the mirrors and their coating chambers are on the summit, and M2 has been coated. So it's the primary mirror being delivered to the summit. There's a picture of sort of the main engineering floor in the summit facility there with the main coating chamber for the primary mirror. And then down at the bottom, M2 has been surfaced and is ready to go as soon as we set up the telescope mount assembly. So that's just some pretty pictures. I also wanted to give you an update on the Lsst observing strategy. So if you remember, it was last year, November 2018, 46 observing strategy white papers were received by Lsst from the worldwide community. And in April 2019, the Science Advisory Committee completed the review and released a report with recommendations for new observing simulations, which are the short form is called OPSIM runs. And by July of 2019, the OPSIM team had released a lot of new survey simulation variations. So there's different footprint options, rolling cadences, deep drilling fields, short exposures during twilight, and the impacts of target of opportunities as well. So if you were writing metrics and you were waiting for the new OPSIM runs to come out, they're out and they're ready. And I put 2 useful links here for you to go and look at all the different kinds of observing scenarios that are there, ready for you to analyze for your science. And the current emphasis of the OPSIM team is on helping members of the community generate and submit metrics to analyze these different observing strategies. So from here, I want to talk mostly about data products. Everything I'm about to tell you is in this one document called the Data Products Definitions document, which you can get to at ls.st/dpdd. And these slides I'm about to show you are quite dense because I know you have access to the slides, and so we're not going to dwell on each one, but they're full of information. You can download the slides and look at them again later at your leisure, but I'll just try to sort of skim across the top and give you a general idea of the different types of data products that Lssd is planning to provide. So here's a sort of a one-side summary of data management, a system overview of how we go from the raw data on the left to the 2 main different types of data products, the prompt data products, which is the nightly or the processing that happens, and then the data release data products, which is the annual data releases. So the 2 types of data products, and then the different access mechanisms. So the prompt data products are released via the nightly alert streams that you probably already know about, but then also via the prompt products database, which are the catalogs, and you can also have access to the images that are reduced in real time. And then the data release data products are sort of released annually and available through the Data Access Center. There's also the way that people will be accessing the data products is through the Lssd Science platform, but there's going to be a whole talk on that on Friday to tell you about the different aspects of the Lssd Science platform, so we're not going to cover that in today's talk. I did want to make the point that the alert packets are the only data product that are public, worldwide public, and can be shared with anyone, anywhere worldwide, and that all the other data products have a 2-year proprietary period, as a reminder. So first, the prompt data products, and I like to emphasize here that all of the prompt data products are a result of difference image analysis. So this is when you have a template image and you have your new image and you subtract the 2 to make a difference image. Source detection is run on that difference image. And any difference image source, which we call a DIA source, with a signal-to-noise ratio greater than 5 is considered detected. DIA sources are associated by location into DIA objects. That's an opposite nomenclature to some surveys. So sources are individual detections in individual images, and then the objects are the collections of sources at a single location in the sky. In the problem pipeline, after that is done, then you do measurement and characterization for DIA sources and the DIA objects. And so the point here is that the source detection is run on the difference image, and each DIA source creates a single alert packet. And that's the public stream of alerts that, for example, Ctf is already doing. The other product of the prompt processing, which is proprietary, are the DIA source and object catalogs, and also the difference and direct images. So I just wanted to go into a little more depth on what is in the alert packet. The little pink thing at the top, it just reminds you again that they're public. Okay, excellent. The alert packet you should think of as everything that Lsst knows about this source that it's just detected on a difference image. So it'll tell you everything you might expect, like astrometry and photometry in the difference image, a shape, signal-to-noise ratio, obviously, and then also a spuriousness parameter, which is like a real bogus parameter, like from any other survey. Within the alert packet, you get all of that information for the source it just detected, plus all of the information with a 12-month history for the DIA object with which that source is associated. And I wanted to point out that this includes variability parameters, which are currently open for input from the science community. So if there's some parameter that you would find very useful to have calculated in real time and be included in the alert packet. We're currently sort of figuring out what those should be. The alert packet also contains all the associated DIA sources from the past 12 months that Lsst has seen, or, and if it was not associated with a DIA object, but instead with a solar system object, so a moving object, that entire record is also included in the alert packet, and then plus the image stamps, which are basically just small FITS files. So everything Lsst knows about the source it just detected goes in the alert packet and is distributed worldwide. I mentioned before that the prompt processing pipeline also generates catalogs and images that are accessible within 24 hours. So the alerts come out within 60 seconds, but then there's additional information that you can access within 24 hours. And in addition to the full images, the things that are not in the alert packet are forced photometry, such as forced photometry and difference images at the locations of DIA objects with detections in the past 12 months. So if you've been watching something, you've been getting alerts on something, and then it fades and it's below signal to noise ratio of 5, you won't get an alert on that anymore, but you can go to the prompt products database and get the forced photometry within 24 hours. So you could link up your TOM, for example, to do that automatically for sources that you're following. The other thing that is in the prompt products database but not in the alert is pre-covery forced photometry for any DIA source that's at a new position where we've never seen an object before. Within 24 hours, the past 30 days, you'll have forced photometry, so you'll know if there was anything below signal to noise ratio of 5 there in the last month. But that's not in the alert, but you can go and query it later. That's something else that a TOM might want to go and get from the prompt products database. And then a slide on moving objects. So this just sort of tells you what are the, for solar system objects, it's all the orbital elements you can get from the prompt products database, and things like, well, I'm not a solar system science, but scientist, but these values probably make sense to, like WES, for example, yes. Yes, so you get all the orbital elements and stuff are also in a separate catalog that you can access within 24 hours. And then this slide is just telling you about the annual data release data products, which includes so difference image analysis is redone with every data release on all the images that have ever been acquired. And so you'll get full survey characterization parameters of all moving and variable objects, plus all the source and object catalogs, the measurements not in the difference images, but in the direct images and also in the image stacks. That because you're going to learn, so you're going to learn about the science platform, which is how individual users will access the Lsst data on Friday morning. But I did want to point out, because this came up in a breakout session yesterday, the Lsst alert filtering service, which is an ongoing development, but it would live sort of in the data access center and be a basic limited capacity alert filtering service where the filters that you would write in this particular environment would be very simple and only be able to filter on information that's already in the alert. So not cross-matching, nothing very computationally expensive, a very simple alert filtering service for people who want to do simple things. So I bring that up only as it's like a small option. We expect most people will be accessing alerts through brokers, though. Right, which is my next slide. It makes sense, yeah. So I think everyone here is probably pretty familiar with what a broker is. When Lsst talks about brokers, it means specifically the ones that are receiving the full alert stream is a broker. Yes, we're going to hear more about brokers, I think, at this meeting. So I did want to tell you a little bit about if you're writing a TOM and you're going to be receiving filtered alerts from the Lsst, maybe you're already doing that now with Ctf. So this is a single slide that tells you the differences between Ctf and Lsst alert packet contents. And this slide was made by Eric Bellum. And there are a couple things I wanted to point out. So one is that if you have been working with alerts now, you'll have noticed, obviously, that Ctf has an alert history of 30 days. And I just wanted to point out that with Lsst, the history, so variability, characterization parameters, and the historical light curve of information in Lsst alerts is 1 year instead. Also, so I said this before too, but in the cross matches, right now Ctf is cross matching to Gaia and Pan-STARRS and putting that cross-match information in the alert before it sends the alert out. But Lsst will only cross-match with its own latest data release. And so it won't cross-match with external catalogs, only the Lsst catalogs. It's another important difference. What else did I want to? Right, so in the second last one there, it says force photometry measurements, which I just mentioned aren't in the alerts. And here it says that, so ZTF doesn't have this, but Lsst, where it says included if they exist, that, for example, would be a case where there was a variable object that was signal to noise ratio greater than 5 for a while, so you had alerts on it for a while. Then it went less, it faded, and it was you did not have alerts on it for a while. When it comes back, and then there is an alert sort of issued on it, that alert will contain the force photometry for all the points when it wasn't visible anymore. So you will be able to get that data later once it comes back over, once it again becomes brighter than signal to noise ratio greater than 5. If you still need more alert information, there's a couple of resources here that we've prepared so that Lsst is prepared for people who are attempting to build brokers and use the alert streams. One of them is a key numbers document that you can access at ls.st/DMTN102. DMTN stands for Data Management Tech Notes, and this is how Lsst releases like very technical information to the communities through this series of tech notes. And this is all the key numbers regarding Lsst alerts. So what's the size of a packet? How many packets will there be per night? What's the average and peak data rates of the alert stream? All that kind of stuff is in this particular document. And then I also wanted to point out this Lsst alert stream frequently asked questions that's been posted to community. And this came out of a workshop that we had in June for people who are proposing to be alert brokers. And it contains a lot of good information about the alert stream, such as when are we going to get real and simulated alerts? Can I get an example of an alert packet schema? All that kind of thing, all that information is in that FAQ. So speaking of brokers and alerts, the broker proposal process is underway. And everything about the process of how the brokers in development apply or propose to be one of the, right now, 5 official brokers who receive the full stream is detailed in LDM 612, which is the document here, Plans and Policies for Lsst Alert Distribution. The first step of that was for broker developers to submit a letter of intent, and we received 15 of them. And all of the LOI submitters have been invited to proceed to the next stage, which is to submit a full proposal to be one of these brokers that receives the full stream. The full proposals we expect to be due in the second quarter of next year with a provisional selection later in 2020. And then after that, broker integration will happen sort of throughout commissioning when alert packets will be released with substantial latencies or maybe in a simulated stream. So that process is ongoing, and if you have questions about it, you can ask me. Oh yeah, that was it. Okay, thanks very much. Yeah.
Perfect. Thanks, Melissa. We have time for a couple of questions.
Did you say whether or not there will be like a simulated test alert stream put out soon, or is that already available?
So, I mean, ZTF is what people should be using if they want a simulated stream. So, but soon, no. So during commissioning, which will be more like 2021, 2022, then they'll start making alert packets in the same schema that the actual Lsst alerts will have and start releasing them, usually probably at first with a very long latency, not quite in real time, and sort of a ramp up from there. But yeah, yep. So yes, so use ZTF now. That's what it's.
So I'd like to jump in at this point because we have a question from the Blue Jeans channel from Francisco. He writes, if an alert is triggered and a subsequent observation yields no additional detections, could we be alerted about this without having to ask for force photometry? This would be useful for candidates near known galaxies, so we would know when to trigger force photometry.
So you get one alert because something has appeared, signal to noise ratio greater than 5, then it drops immediately. No more alerts. But he wants an alert packet for the non-detection, it sounds like.
Yes, I think so. I think it's referring to a case where you have an alert. He says yes, what you just described.
Yeah, okay, yeah, yes. Yeah, okay, so I think that there will be alerts for non-detections like that. I think you just get that information another way. You just have to go and query the prompt products database. There's not going to be alerts for anything other than signal to noise ratio greater than 5 detection. Yeah.
Okay, that's clear. Thank you.
Yeah.
Going to be a loss anyways, right?
It's going to be what?
I mean, you're going to have a lot of alerts, and if you start putting out alerts for non-detections, and
Yeah, it might get a little too much.
Where's information about light curve features can be found?
Information about light curve features?
Yeah.
Yeah, so you get it two ways. One, the alert packet itself will have variability characterization parameters for the 12-year history that is included in the alerts. So we're still figuring out what features those should be, like amplitude, a rise, periodic and non-periodic features.
This is unknown. What
There's sort of a default list of things we could use. But yeah, if you have particular features that you find are very useful for like machine learning classifications or your classifier, then...
Where can I find information? What features will be provided?
From me, pretty much. Let me see if I made an extra slide about that particular question. I don't think that I do. No, I don't have a slide on that. I do on my laptop. Yeah, ask me later and I'll show you what Eric's got going for it. Yeah.
right, we have a lot of questions. Let me make a quick answer. So that the plan, what we're going to do next. So we'll have 10 minutes to discuss what we are going to discuss in the next 45 minutes after that. And one of the suggestions for that discussion is Q&A to the surveys. We don't have too many Lsst people here, unfortunately, but there are a bunch of Ctf people here. So if you still have questions, I suggest to move that onto that discussion. We're a few minutes behind schedule. So let's thank Melissa once again. So, by the way, Melissa, who is there? Are there other people from Lsst here, or is it basically only you who can be asked questions?
Yeah. Gregory will hopefully be here on Friday.
I see.
Yeah, I'm Rachel.
Okay, so once again, we now have about 10 minutes to discuss what we're going to discuss next. And after that, we'll split up into smaller groups and discuss that. Basically, the summary for the first two talks of today, we are already dealing with zillions of alerts. And I just looked up some quick stats. So as of last night, ZTF generated 2.4 million alerts in the past 7 nights, and 75% of those had a real bogus score greater than or equal to 0.5, meaning that those have a probability of 98 to 99% of being real. It's mostly variable objects, but there's lots of transients and asteroids in there as well. So, exactly. But it's kind of a typical situation because we've put out this. No, that's everything. That's everything. So, yeah, as Matthew said, we've put out 182 plus million alerts since last February. So we started doing that before the public stream was made online. So that's number one. Number two, it's only going to get worse or better depending on how you look at it. So easily add a couple orders of magnitude when the Lssd, to the number of alerts when the Lssd comes online, which is very soon. That's something that surprisingly many people don't appreciate to the extent that they should. So for the discussion, I'm suggesting sort of several high-level things. So first of all, if you still have questions about Ctf or Lssd, I would suggest to have a dedicated group of people for that, unless Melissa objects strongly, because there seems to be a lot of questions and probably more questions will pop up. Then, since we are at the TOM meeting, I think it's very important for us to discuss the role of TOMs as kind of a buffer between brokers and follow-up facilities. And I think, so that's kind of my personal takes on that, and I think that there's a bunch of things that would be nice to have by default in the TOM toolkit that are currently not there. For instance, we've already seen examples of where you run a query on the broker and you get a table and you can look up all the alerts one by one, but that's not particularly helpful if you have a table with 10,000 rows or something, or like 100,000 rows. So I think, so that's bullet point number 3. So what I call the bulk visualization. So I think we as a community need some good UX designers who know how to work with big data, because you really want to visualize that kind of stuff. There's no way you're going to look at the table or inspect them one by one. So there are ways to do that. We just need to do that, and it would be nice if that feature was available out of the box. Also, a more streamlined consumption of alert streams, so to say, would be nice, without having to, I don't know, a job queue available by default, so on. And also, brokers are very nice, and they will be providing lots and lots of nice ML, machine learning classification features, but that still need not be quite enough for some people. So it would be nice to have some built-in support for some custom downstream classification and machine learning models built into the TOM. Or I mean, it should be easy to plug that in. Not only at the stage when you already got the data from your follow-up facilities and run some data pipelines. And that's one thing I think is worth discussing. Then another thing is just service and follow-up in general, and that was announced in the sort of the topic for today's first session, is how we go about coordination between service and follow-up and potential co-service strategies. And I left some space for miscellaneous stuff. So if you have any other ideas, or if you think, now I'd like to hear from you. What do you guys want to discuss?
So thank you to everyone who has added to the TOM ideas page. We have quite a substantial table of ideas on there as well. So just to run through them quickly, we have a proposal to have a non-conference session on Antares writing your own filter. There's a discussion of observation priority versus the probability of observations being executed. There are different systems for this. There's a suggestion for the kind of request to the telescope representatives, which to introduce the instruments that will be available in the proposal of call, which I think we'll come to in the later sessions. There is an idea to use universal cross-matching programming interface inside the TOM from Konstantin, and another one using the TOM as a user interface for human-assisted machine learning. And of course we mentioned the proposal pitches earlier, and lastly a proposal for TOMs and their integration with the Zooniverse and other citizen science projects. So any or all of these topics are open for discussion. So it's up to you folks. What would you like to do?
Yeah, so I think what, thanks Rachel, so I think what you just mentioned fits into the second sort of thing, and I would probably suggest, all right, let's do a quick hands up. So who's in for the Q&A for service and alerts? Okay, good many. Second part, a whole lot of people. And what about service and follow-up? Quite a bit of people. You know what? I would probably suggest to merge Q&A and service and follow-up, because we have about an hour, or a bit less, 50 minutes or something to discuss. And yeah, people to answer your questions should be available throughout the meeting, so just feel free to talk to them if you still have unanswered questions after that. So Rachel, could you please say what rooms are available for people?
So the rooms are the same breakout rooms that we've been using for the last couple of days. So the
Yeah, so let's discuss this in the library, and that's in the conference room. Right. Thank you.
And can each group assign its
Yes. So we'll be back here in 50 minutes, so 10:45. So that named spokesperson will please present what the outcome of that discussion was. So see you in a bit.